Alright, we're continuing on with freefall. The last video we looked at an object falling, just falling straight down a cliff. And now we're going to do something that is a little bit more complicated, and that is we're going to toss the ball up and then have it fall. So I have here a nice little overhead, and it shows a person who has a ball. They throw the ball up, it peaks, and then it drops back down to the same height at which it was released. And now that is important, the same height at which it was released. If it does that, then we have symmetry. And the symmetry is perfect. It makes everything easy. And I'm going to teach you how to break this down in a symmetrical way. And so what's true for one side is going to be true for the other side. So I'm going to take this example and I'm going to write it on a piece of paper, and before we do the math, we're going to talk about the concepts, what's actually happening when this ball is going up and then coming back down. So I'm going to have my ball, and it's going to go up, and these, what I'm drawing here, are vector arrows. And you notice as they get higher, the vector arrows get smaller. These vector arrows indicate velocity. And I should probably make this one really long. So I have that one. Then it gets shorter and shorter and shorter. So these are velocity arrows. And as the object gets higher and higher, these arrows get shorter and shorter. That indicates that the velocity is getting smaller and smaller until at that point there is no velocity. The ball momentarily passes through zero, meaning for a fraction of a second it stops. And then the direction turns around and it comes down. And these velocity arrows are getting larger and larger and larger. Hang on. Light went out. They're getting larger and larger and larger. And if you take a look at these velocity arrows, they should be closely resembling the same size, because the change in the velocity is the same. And from the last video, you know that the change in the velocity is due to gravity, g. 9.81 meters per second squared. Now, acceleration, gravity included, is a vector. It has a direction associated with it. So the direction of gravity always points downward, right? So depending on what you declare as positive and negative, what direction you say is positive and what direction you say is negative, that right there will have, when you do that, you can assign the value to g. I'm going to declare that my upward motion is positive. Having declared that, that means the downward motion is negative. So whenever I work any problems, that means g goes in as a negative value because it always points down. And I declared that up was positive. So you have to pay attention to the direction. It's a vector. Alright, so I have a ball, I'm going to toss it up. Here's some things that must be true. In order to get the ball in the air, this velocity down here cannot be zero. It has to be some non-zero number. If this velocity is zero, then that ball never gets into the air. It just stays in your hand. So that must be true. And because this is nice and symmetrical, whatever the velocity is here, it's also the same velocity here when the ball comes back down at the same location. Again, that's important. It has to be at the same height in order for this to be true. So that's when we look at the action going up and coming down. That the initial velocity on this side is the same as the final velocity on that side, except over here it's some non-zero positive number, and over here it's some non-zero negative number. Positive meaning pointing up, and negative meaning the velocity points downward. So that is the symmetry of this. It's really nice. It makes the problems really easy. Let's take a look at the top. Now when the object gets to the very top, like I said, momentarily it passes through 0. And I'm not going to identify it as initial velocity or final velocity because it depends on how you look at the problem. I'm just going to say what we know for sure is right here, that the velocity is momentarily 0 meters per second for a fraction of a second. Now the way to diagnose this is you can either look from the bottom going up to the top, or you can look at the top and coming down to the bottom. To me, I prefer looking up here and then coming down there. Because if you think about it, if I throw the ball up, let's say I throw the ball up a height of 50 meters, how much does it have to fall back down? Hopefully you said 50 meters. If I throw the ball up and it only goes 25 meters, how much does it have to come back down? 25 meters. So there's some symmetry here, which makes it nice. I like to look at this scenario from the top down, because when you do, that means the initial velocity, when you look from the top down, Wn, when you look from the top down, that means the initial velocity is always 0. With the initial velocity being 0, always 0, then if I come back to my equations, that means this portion of the equation doesn't exist, because 0 times anything is 0. That right there cuts your equations in half. So I like to look from the top coming down, and then once I get my answer, I can apply some concepts, some things I know to be true. So that's what I like to do. If you like to look from the bottom to the top, you can. It's a bit more work. You have more variables to deal with. You have more keystrokes in the calculator, which means you could run into some error. I like to look from the top coming down and then apply some concepts here. The other thing in the symmetry is the time. If it takes 2 seconds to go from the bottom to the top, it takes 2 seconds to fall back down to the bottom. This is the symmetry of the motion, and it makes everything 0. So the time to the top has to be the same as the time to the bottom if it lands at the same height at which it was released. And that's a very important caveat that you must remember. And for pre-AP, that is true. We'll make it simple. It is true. If it's AP, then you have some things that you have to apply, and of course, when you come to class, we'll talk about those implications and apply them and do some sample problems. But let's take a look just where the ball is released from one height, it goes to the peak, then it turns around and it comes back down to the same height. And I'm going to look, for me, always from the top down, because when you do that, you eliminate the front half of your equation and it makes the math easy. So I have some questions here. Let's do some scenarios. Let's say I take a ball. First one, let me write a question down here. What is the initial velocity? velocity if the ball goes, let's say, 5 meters. So what is the initial velocity if the ball goes 5 meters? Well, let's see. I've got a couple of things that I know. I know that gravity is negative 9.81 meters per second squared, and I'm saying negative because I already declared that up was positive. Since gravity points down, it's negative. I know height. I know the ball has to travel 5 meters. That's how high it goes up. If it goes up that height, then it has to come down that height. Because remember, I'm always looking from the top down. Displacement is also a vector, which means it also has a sign. And then it wants to know what is the initial velocity. Well, if I know the final velocity over here, it's got to be the same as the initial velocity over there if the ball goes up and returns back to the same height. And for pre-AP, it does that. So if I can calculate the final velocity, I know it's the same as the initial velocity. So I have my givens. Let's see, I have Vf squared is equal to Vi squared plus 2g delta y. If I can calculate the final velocity, I already know the initial. If I can calculate that number, I already know this one. They're the same. Since the initial velocity is 0, because I'm going to look from the top down. If I look from the top down, the velocity starts at 0. So I can go ahead and assign this as 0 meters per second. This is what is the initial velocity if the ball goes this high. Be careful, because the initial velocity I'm putting in down here is not that one. It's this one, because I'm looking from the top down. So I will plug in, oh, there goes the light. Let me hop up again. So I know that Vf is equal to the square root of 2g delta y. This is 0. There it is right there. There it is right there. So Vf is equal to the square root of 2 times negative 9.81 times negative 5. What happens is you'll forget to put in one of these negatives. If you forget to put in one of the negatives and you try and take the square root of a negative number, you're going to get an error in your calculator. That right there should tell you, look at your values. Something went wrong. So I'll call this roughly 10. I don't have a calculator, but we'll call that's close enough to 10. So 10 times 5 is 50, and I multiply that by 2, which is 100. So I'm going to say the final velocity when it comes down is approximately 10 meters per second. Well, if that's the final velocity down here, it's got to be the same as the initial velocity up there. So the initial velocity is approximately 10 meters per second. So this is the thought process. To me, is the easiest, is to look from the top coming down. If you look from the top coming down, the initial velocity is 0. And then everything that's true on this side of the equation, or this side of the motion, is true for this side of the motion. If the velocity here is 10 meters per second, then at that same point on this side, it's also 10 meters per second. If here it's 38 meters per second, then right here it's 38 meters per second. That's the symmetry. That's the beauty. We will do some more. We'll do some sample problems. You always have UT homework. I have a lab set up for you guys so you can verify that the velocity does change as the ball drops, and that this equation here, V is equal to delta x over t, does not apply. That V is equal to delta x over t, that does not apply, which is why I did not give it to you when I listed your equations in the last video. It does not apply. It doesn't, so don't use it. Alright, if there's no questions, good luck. I hope it makes sense. Otherwise, write your questions down and we will talk about it when you come into class. Good luck.